Good morning, everyone. I'm Jason Bakos from the University of South Carolina. Today I'm presenting our work on high-rate machine learning for forecasting time series signals. This is a collaborative effort involving our team in South Carolina and David Andrews and Mao-Chin Huang's team at the University of Arkansas. Our objective is to develop a system that can accept samples from a time series signal, and for each sample forecast the future state of the signal, as well as continuously training the model to allow it to adapt to unexpected changes in the signal dynamics. We have three main performance metrics. The first is forecast accuracy, the second is retraining time, which is the time required to recover from a change in the signal, and the third is latency, which must be no more than the sample period to meet the real-time constraints. In this paper, we present our algorithm as well as a high-level synthesis-based and overlay-based implementation. This slide illustrates the challenge where the blue line here represents our signal, the green dot is the most recently read sample, and the red dot is the forecasted value of the future state of the signal, which is the future in the sense that it is f samples into the future. So in this case, we define f as the number of samples in the future we want to forecast, and of course the error would be the difference in the forecasted value versus the actual sample, which you won't know until the signal catches up with the forecast. This type of forecasting can benefit applications that perform control of active structures. There's examples of this would be active vibration dampening for electronic components on aircraft, or deformable mirrors, which like the ones used in telescope to compensate for atmospheric distortion. In general, forecasting time series signals only using the past state of the signal is only possible when the signal is periodic. So one way to perform forecasting is to just record one period of the signal and play it back. But the problem with this approach is that we don't assume any prior knowledge of the signal's period. And also, even if we did, that period would impose a lower limit on the retraining time. And also, the period may change unexpectedly whenever you have a change in the signal dynamics, which we refer to as a non-stationarity. So for this reason, we've chosen to use a feed-forward neural network-based forecaster that accepts a sequence of recent samples to produce its forecast. We define the number of past samples used as the input to the model as h, or the history length. And while we're using the model to make forecasts, we're also continuously training the model in real time. And in order to calculate the loss to back propagate, we need to perform a second forward pass for each sample to predict not the future sample but the current sample using samples received earlier. The data set that we used for characterizing our designs was gathered in Austin Downey's lab. He's in our mechanical engineering department by using an electromechanical shaker to stimulate a steel beam, the acceleration of which is measured with an accelerometer attached to the end, or actually in this case the middle of the beam. We collect data for 20 seconds and insert a non-stationarity into the shaker input at around the halfway point. The spectrum of the measured signal is shown in the lower right-hand corner, and that you can see peaks corresponding to the excitation signal components, but there's additional components that are created by the vibration modes of the beam. So when deploying our forecaster, vibration measurements are read and their native sample rate R, which in this case is 51.2 kilohertz, and then they pass through a stage of subsampling to a new sample rate of R sub S, and quantized to a word size of n. R sub s and n are selectable parameters, as well as h and f. The samples are shifted into a serial to parallel converter, which is long enough to expose the most recent h samples seen, as well as the h samples ending with sample t minus f, which are the inputs used for each of the two forward passes. The most recent samples produce the forecast, and the less recent samples produce an estimate of the current sample and is used to compute the loss for the backpropagation, which is then subsequently performed, and all the weights and biases are updated. All of this workload is performed within a single sample time, which is 1 over r sub s samples. So we have two primary performance metrics that we associate with the parameterization of the forecast model. We have the error. First, we calculate the error signal as the difference in the forecasted value versus the original signal at its native sample rate, after correcting for the phase difference caused by the forecast. Then we calculate forecast accuracy as the log of the ratio between the power of the error signal and the power of the original signal, and multiply this value by 20 in order to express this value in decibels. The second metric is retraining time, which is the amount of time needed for the network to achieve half of its steady state accuracy after a non-stationarity occurs. To compute this, we first fit the absolute error versus time to an exponential curve a minus b times e to the negative c times t power, and then we find the center of gravity of the area under this curve, which is log of 1/2 over c. In this example, you can see that we've split the area under the curve into 2 equal halves, colored green and red, which occurs at t equals 0.27726 seconds. Both of these performance metrics are affected by three main parameters, namely h, which is the number of inputs, the hidden layer size. We use a 3-layer network here. Hidden layer size is s, the chosen subsample rate r sub s, and the word size n. Note that the amount of historical information is the amount of history in terms of time is h divided by r sub s. Ideally, this value would be less than the period of the signal if one exists. We performed several parameter sweeps to evaluate the impact of hs and r sub s on accuracy and retraining time. In this plot, we show the signal noise ratio versus h and s. So h is the horizontal axis and s are the different curves here. All of these data points use an r sub s of 2500 hertz. The dotted line on the plot shows the accuracy ceiling measured for the subsampled, which is measured as the signal noise ratio of the subsampled signal versus the original signal. So the closer we get to this line, the closer the forecast model is to being perfect. As shown in the plot, accuracy improves with h and s with an approximate point of diminishing returns at around 40 milliseconds of history. Since these results were generated with a floating point, we also examine the impact of quantization. So this plot shows the accuracy versus h with 50 hidden neurons at 2500 hertz when varying the word size from float to fixed point, 8 bits down to 4 bits. The results show that both 7 and 8 bits are nearly equivalent to float in terms of signal noise ratio. So we generally use 8 bits in our deployments. When plotting retraining time versus h and s, which is what we have got here, the data is noisy and it's kind of difficult to find a trend. This is because for a given number of hidden neurons, making the network more accurate by increasing h can also make it slower to retrain. But there's cases where the retraining time is less than 10 milliseconds. But since we're currently limited to using fixed learning rates, we haven't found a way to bound the retraining time. We also examined the impact of different quantizations on retraining time. In this case, it's also difficult to find a trend, except that once again, 7 and 8 bits perform similarly to floating point. Now, when we increase the subsample rate beyond 2500 hertz, we have to correspondingly scale up the h, the history size, the number of inputs, to ensure that the achieved accuracy follows the same trend as the accuracy ceiling. Generally speaking, the value of h gives around 150 milliseconds of historical information, at least the h's that we chose. So for these results, we kept the number of hidden neurons here fixed at 50. So we built our high-level synthesis-based implementation using Vivado HLS 2019.1. The workload here can be decomposed into 6 kind of parts, but only 3 of these comprise nearly all the execution time, namely the 2 forward passes, and the hidden layer weight update. We implemented each of these with a pipelined loop. The other phases are just fully unrolled loops. Each of these fits the pattern of each of these loops, though, that we've got that are colored orange, fit the pattern of a vector matrix multiply. So their throughput is limited by the RAM bandwidth, but we achieve the maximum possible throughput for each of these loops based on the maximum number of BRAM banks that's supported by Vivado HLS, which is 1,024 banks. However, since each of these loops must be performed sequentially, the iteration latency of each adds to the overall execution time. So in this case, the iteration latency scales with the reduction size in the hidden layer, or the summation size, which is equivalent to the number of inputs, or in this case, H. That is not the case, though, for the hidden layer. The hidden layer weight update does not have a reduction, so it has a much smaller iteration latency. Our HLS design targets a Vertex UltraScale Plus VU9, for which we can achieve an Fmax of up to 484 megahertz. The BRAM and DSP usage of the design is limited by the to the RAM allocation given the maximum number of banks, assuming the value of S is less than 512, and of course we're only using, generally speaking, 50 neurons in the hidden layer. So none of the designs exceeded this allocation limit. However, we do max out the LUTs with our largest design. To evaluate an overlay-based approach for our proposed system, we used an existing overlay architecture from David Andrews' group, which is called the SPAR2 array processor. It's a 2D array of 1-bit processing elements that perform collectively to perform multi-cycle arithmetic and arbitrary precision, but at with massive parallelism. So for an 8-bit word size, a multiply add requires 96 cycles, and an n-way reduction requires log n times 16 cycles to perform. The architecture is comprised of a 4x4 block of processing elements associated with each BRAM as shown in this figure. The array is scaled up by instancing a 5x5 grid of these blocks, which are organized into a tile, and a 5x5 grid of tiles that comprise the overlay, which gives 10,000 total processing elements. PEs can exchange values with a neighboring PE, allowing intermediate results to be passed from one PE to another in the north, south, east, or west direction. And the array provides best performance when the input matrix can be mapped to a single entry in the RAM, which is the case for all but the largest model. David's group added additional data paths to support backpropagation, specifically a copy instruction that moves data from the first row of PEs to the last column of PEs, and as well as from the last column to the first column. As compared to the HLS-based implementation, the overlay is able to exceed that 1,024 bank limit that's imposed by Vivado's HLS loop scheduler, but it suffers from having multi-cycle multiplies and a lower Fmax of 330 megahertz. Now these plots show the minimum required effective bandwidth, minimum effective throughput and on-chip memory bandwidth needed to achieve real-time operation of each of the forecast models, each associated with an R sub S value or sample rate on the horizontal axis. Since the operational and memory workload is almost the same, the plots are basically the same. The yellow line shows the minimum needed, minimum that's needed for real-time operation and the corresponding at the corresponding sample rate, while the blue line shows the performance achieved by the HLS implementation, and the overlay, and the orange line shows the performance of the overlay. The HLS implementation is generally much faster than what's needed, but while the overlay achieves its real-time constraint for all but the largest 3,200 input model. So to conclude, we use a fairly simple machine learning method-based approach to simultaneously forecast and train a model for time series data. We showed 2 implementations. Achieving real-time performance depends mostly on sustained memory bandwidth across the 2 forward passes, followed by a weight update. Our current work is focused on finding a way to dynamically adjust the learning rate of the model in order to improve retraining time, and to move from an MLP. We were also working on moving from an MLP to an LSTM-based model, which would eliminate the need for scaling the age parameter with the sample rate. So thank you very much.